In this video, I will demonstrate the design procedure for a microstripline to SIW, which is a substrate integrated waveguide transition from the scratch. So let's start. First, we need to build a new project. So we can use a new template, and we are going to use this microwaves and RF optical. So here we have a different template we can select. In our case, we are going to use this circuit and components. Just double click. For the workflow, we select this one, planar, coupler, and divider. Since in our case, we do not care. It is a planar structure, so we select this one. In my simulation, I will run it at a frequency domain, so I select the frequency domain. In this page, we can set the units. I just use the default one. The working frequency, since the working frequency I'm interested in is at 28 GHz. If you watched my others video, you will know I'm working on a tutorial project for band 28 GHz antenna array. So this is also part of that project. That's why the center frequency is 28 GHz. So I will set the simulation frequency start from 26 to 30 GHz. In this case, this is not a radiation structure, so we only care about the E field and H field instead of far field. At the beginning, we can only focus on the 28 GHz. So we just select the 28 GHz E field and H field. Go to next. Now we've already selected which template we are going to use to build our structures. So just click finish. So here we've already built a new project. Next step, we are going to build the 3D structures of the design. So here we can use this, the basic structures we used is this brake and the cylinder. This brake we are going to use to build the substrate, the copper, the microstripline, and this cylinder we are going to use it to build the VS for the substrate integrated waveguide. So let's start. First, click brake, and then we just double click, and double click. So now we build a structure. I will name it as substrate 1. Maybe you will wondering how I get these numbers to build the numbers I used to build up the 3D structures. Don't worry, I will explain to you how I get these numbers later. These numbers is calculated based on some theories and some experience formulas. The theory is a little bit different from reality, since the theory is simplified from the reality. So the initial value we calculated from experience formulas and the theory calculations may be a little bit different from the best performance in reality, but it is good enough for a start point to optimize it. So in this 3D structure build-up, I'm going to use variables to stand for all the parameters, which is easier for the next step for the optimization procedure. So here we just build the substrate. The width will be minus sub subwidth 1 divided by 1. So this will be subwidth 1 divided by 2. Sorry, this is minus subwidth 1 divided by 2. This is a subwidth 1 divided by 2. And in the z direction, it will be start from 0 to minus subless 1. In the z direction, it start from 0 to minus substrate height. So the component I will call it SIW. And the material I will use, we can use the Rogers 6002. We have two different materials. One is the lossy-free, one is the lossy one. So I want to make it more closer to practice. I will use this lossy material. So we just select it and load it. Now we preview it. The substrate width I used here is 8 millimeters. So the length is 20. The height is 0.254. Okay, so just click space and 5 space. Okay, 5 space. Now we have the substrate. So you can see it here. So we have the first substrate. Then I'm going to build up the bottom copper. So just click bricks, then double click, double click, double click. We name it as copper bottom. The dimension is defined here. This will be the same as substrate 1 divided by 2. This will be substrate width 1 divided by 2. This will be minus substrate length 1. This will be 0. So this starts from the minus substrate height to the substrate height minus the copper thickness, which is 0.017. So the also belongs to the components. Components belongs to SIW. The material I will use just the copper. So here, copper. Okay, loading. If you are not clear your structure is correct or not, we can use preview to preview it. Okay, it looks like what I expected. Click OK. So now we have the bottom copper and the substrate. Next step, I'm going to build the top layer copper. What I'm going to do is I just duplicate this. I just transform this bottom copper and copy and transform this bottom copper to the top layer. So first select this bottom copper and then use transform. Since we want to have a copper, the original copper as bottom and then duplicate it at the top layer. So we need to check this one, copy. And the direction is in the z direction. The distance will be the substrate height plus the copper thickness, which is 0.017 plus 0.017. Now preview it. Okay. So look at here. We have a bottom copper substrate, top layer copper. I want to make it easier to recognize from its name, so I change its name. This will be copper top. Okay. Now we have the basic substrate, and then I'm going to build a VS. So I will use a cylinder to build the first via. Just double click, and set the height. Then press ESC. Okay, so I will name it as via left, which stands for the via at the left, at our left hand. So the diameter, it will be d divided by 2. And the location, this will be the r divided by 2. So this AR stands for the width of the SIW, which is the distance between the two rows of the vias. This will be 0. Z direction is start from minus substrate height minus the thickness of the copper, which is 0.017, and then stop at the top copper, which is at 0.017. Okay, and it also belongs to SIW. So material is copper. Let's preview it. The diameter is 0.4. Okay, so the SIW width is 4.5. Don't worry about these numbers. Let's just build up the 3D models first, and I will explain how I calculated each numbers. Okay, click OK. So preview. Oops. Okay. Okay. Looks like I made one mistake. So copper. Sorry, 1 second. Let me double check it. Definition. Okay. So first via. Okay, let's clear this pickup. So we have a left vias. Let's build up the right via. So I will just mirror it and duplicate it. So first select this via, and we use mirror it, then duplicate. So the mirror plane normal is, I think it is X. Yeah, it is X. So preview it. Yeah, now we have this vias. Rename it to be via R, which means the via at our right hand. So now we have two vias. Next step, I'm going to duplicate them along this Y direction. Then I will have two rows of a via, which is the key components for the SIW. So select these two vias, use transform. So copy and transform. Okay. So distance we call it the pitch. It's the center to center distance between two adjacent vias. So the repetition factor will be the substrate length divided by the via pitch. So let's preview it. The via pitch, I set it to be 0.6. Okay, now we have all the vias here. Click OK. So now you can see we have the substrate and the 2 rows of vias. So basically we already have the SIW. But in reality, you know, when we need to use a microstripline to feed the electromagnetic signals, right? So what we are going to build next is we are going to build a 50 ohm microstrip line and then a transition which connected the microstrip line to this SIW. So let's start. So first I'm going to drawing a polygon. So select some random numbers, 1, 2, 3, 4, 5. Okay. So here we are going to define the dimensions. Name, we just use the default name Polygon since we will delete these lines later. So start from this point. This will be the width of the tape. I just call it WT, stands for the width of the transition of the tape. Divided by 2. This should be, it is 1.33. This is 0. The second point is the width of the microstrip line. I will 50 ohm microstrip, and I will call it micro width divided by 2. So this will be 0.647 for a 50 ohm microstrip line. And the length should be the length of the tape. I will just call it tape length. Tape length, it will be 0.124 millimeter. Okay. So the third point is the width will be minus microstrip line width divided by 2. This will, the length will be the tape length. Okay. Oops, sorry. Made something wrong. Let me see. Tape length. Okay. So this will be the minus tape width or transition width. Minus tape width divided by 2. This is 0. So how about this one? This one should be okay. This should be minus tape width divided by 2. This is 0. Okay, good. Now we have this polygon. This polygon is just a 2D structure. We need to build a 3D structure, so we will use this function extrude. And then we need to select the polygon point. Just press P to help us select it. Okay, first point, press P, second point, press P, third one, press P, fourth one, and press P. Let's go back. Okay, and then now we can decide the height of the extrusion. Okay, we just double click it, we name it as a tape. So the height, it will be the height of the microstrip of the copper, which is 0.017. And we change the components to tape. It belongs to tape. The material is still copper, so preview it. Perfect. This is what I want. Now you can see. Now we have these 3D structures. So we do not need this polygon anymore. We can delete it. So curves, polygon, yeah. So this one we do not need it. We can just delete it. Okay, perfect. Next step, I'm going to build the 50 ohm microstrip line. Since this width is already be the 50 ohm microstrip line, what I'm going to do is just select this face and then use this function to extrude. We'll call it microstripline. Microstrip. The length will be microstripline length. Okay. So just preview it. The length is, we can set some random number. It is not so critical for the microstrip line length. I just set 6. Okay. So now we have it. Just click OK. Now, next step, we have top copper. We need to extrude this substrate. So we do it a similar way. We just press F and then double click this face. We use extrude function. We call it substrate 2. Substrate 2. Okay, so the length will be the tape length plus the microstrip line length. So plus microstrip line length. So this micro length preview. Okay. Hold on 1 second. Yeah, we need to change the material to the Rogers material. Click OK. For current stage, we just use none to all. Since this is metal, this is dielectrics. Okay, and then we need to build the bottom copper. We do it in a similar way. So press F, select the surface, then extrude it. Call it copper bottom 2. Okay. So the length will be tape length plus the microstrip line length. Microstrip length. Okay. Preview. Okay. Press. Okay. Press none to all. Oops. We forgot to change the material. It's okay. So what we can do, we go to, since this belongs to the tape, go to here. This is the copper bottom. We just change it to copper. I'm going to select this one and drag it to the copper. Okay, so now you can see it is copper. Okay, press space, press 5 space. So now we have a substrate integrated waveguide here, and then this is the transition. This is 50 ohm microstrip line. So next step, I'm going to mirror this structure, then we will have a back-to-back structure. Let me show you how to do it. So select this one and this one. Select the current structure. We use transform. First, I'm going to copy and mirror it. So the mirror should be 180 degrees. oops, sorry. This will be, okay, let's preview. Okay, this is what I expected. Now to R at this stage. And then I'm going to relocate it. Oops, forget one thing, one important thing. Okay, goes back. Okay, let's have a look here. Okay, no duplication, no duplication. Yeah. So let's do it one more time. Select this. Now select the whole structure. Then use the transform. I'm going to copy and then mirror the copy. So the copy, we define the mirror plane. So we define the mirror plane. What I forgot is I want to set the duplicated structure in belongs to new components group. So I just duplicate, just give it a name and then preview. Okay. Now to R. Now I need to, so this is the duplicated structure. This is the structure we built it before. So what we want to do is we want to relocate this. We want to relocate this duplicate structure. So select this duplicate structure and use transform. We do not need to copy it this time. We just need to relocate it. We can use this use our mouse to drag this arrow to change it, the location. Roughly location. So we can specify the translation vector here. I know the distance should be the substrate length 1 and times 2. Okay, preview, perfect. Yeah. So now we have the back-to-back structure. So here we have a, so if we zoom in, we have a 50 ohm microstripline and then transform this 50 ohm microstripline to this substrate integrated waveguide. And here we have the structure in the reverse order. We have a substrate integrated waveguide, and then we have the transition to change the impedance to the 50 ohm microstripline. So this is not a perfect structure, but we can optimize it later, such as this one we need to adjust it a little bit to make it look better, since in reality it is hard to machine it in the factory. But for simulation, to prove our concept or demonstrate how to build this substrate integrated waveguide and how to design this microstripline to SIW transition, it is good enough for. So now we need to save this project. Let me save it here. So this, I will call it SIW to microstrip tape. The first try. Okay. Next step, so now we finished the 3D structure build up. Next step, we need to set up the excitation port. So here, before we do that, I need to show you a tip. So click home, go to micro. We can calculate, go to solver, and then go to the ports. We can calculate the ports extension coefficient. which is important since we are assuming the port, the excitation port is 50 ohms. So the width is this is the width of the microstrip line, which is 0.647. Okay, the height is 0.254, which is the height of the substrate. Then the permittivity of the substrate is 2.94. Then we can calculate the extension coefficient, which is 4.2. Okay. Yeah, this coefficient can be a little bit relatively larger than the recommended one, but we highly recommend to not make it smaller. Okay, so we select this, press F, select this surface, then go to simulation. We will going to use a waveguide port to exit. Okay, so here define the extension distance. This will be the microstrip width. Okay, just copy this one, paste. This is just this is the substrate height. Preview. This is 4.2 as the coefficient. So preview it. Okay, good. This is what I expected. So we have one excitation port. We do it on the other hand. On the other end. So here, just select the face. Then waveguide port. Do it a similar way. Paste. This is the height. Oops, sorry. I made a mistake. This should be the height. This should be the... Oops, sorry. That's correct. Oh, memory. Okay. Oops. Oops. So let's do it one more time. This should be this one. Yeah. Should be this one. Should be paste. This should be the height. Preview. Okay. Let me double check it. So the solver ports coefficient calculation. Oops, sorry. Yeah, this is the height, not the width. So we need to change it. How to change the dimension setting of the excitation port? We just go to ports here. This one. So this will be coefficient times height. Okay. Okay. Yeah. Normally this width should be several times of the height and the width. So it looks correct. Now we need to make a correction for the port 2. So we do it a similar way, just paste, then click OK. Yeah, that's it. So now we have the 3D structure. We defined the excitation port, and what we're going need to do next is just to set up the simulation. So here the number of data samples seems too less. I want to increase it. So 2000, since my okay. Yeah, my simulation range is 4 GHz. I should set it to be 4000. So 1.41 megahertz. That's good enough. Click OK. Start. So we just wait for the simulation to finish. Now the simulation has done. Let's have a look of the results. Let's first check the S parameter. So what we have here, this is S11. Generally speaking, the initial values give us a decent values. So at 28 GHz, it has a good good S11. And let's have a look of the insertion loss. So here, the insertion loss, it's around 1.2 dB. So let's have a look. What's the length of the structure? Okay. Press P. Dimensions. So the total length of the back-to-back SIW is around 60 millimeter, and the insertion loss is around 1.2 dBm. 1.2 dB. I think this initial value gives us a decent performance, even though there's still some. I think there's still some space to improvement the performance. So first we can, as I mentioned, the width of the transition is calculated based on experimental formulas. We can use the parameter sweep to find a better solution for the width. The second thing we can try is, okay, let me mark out which we can try to optimize. So this is the first parameter we can try to optimize. We can try to increase and decrease it a little bit to compare the performance. The second thing we can try to optimize is the one second. So pick up. Yeah, the second thing we can try to optimize is the length of the tapered microstrip line. And also we can try to manually adjust these two vias and these two vias, either combine them together or try to change the length of the whole structure. But I think, yes, there's still some space to improve the performance, but this one gives us a basic idea how to design the substrate integrated waveguide and how to simulate to check the performance, and also demonstrated how to design the microstrip line to SIW transition, and how to check the performance of the whole structure. So later I will show you guys how I get this initial numbers, how I calculated them. Okay, thank you. Thanks for your watching. See you next time.